Let me first start from acknowledgement my co-authors, Satish Karra, Scott Painter, Jeffrey Hyman, Harry Viswanathan, Carl Gable, and the whole computational earth science group at Los Alamos National Lab, who made a great environment to work in, and US DOE for financial support of the project. So, in spite of the fact that a couple of decades hydraulic fracturing being used for natural gas production, there are still many unknown things. And in this presentation, I would like to focus on one of them, where we want to look at production curves. So this is a plot of MIT study. There we actually have a production curve of 3 sites, 3 reservoirs, and the behavior of curves are pretty similar. So in the first couple years, the 60% of natural gas was coming out, and then there is a rapid decline of a production curve and a long tail. So we use Discrete fracture network model, DFN works, this is how our software called, to look at the reasons why the decline is so fast, why the tail is so long. And in this presentation, I will focus on how fracture aperture affects on production curves. So let me start from introducing to you our discrete fracture network model. We heard here a lot of experimental studies, so here is a modeling. So here is an example of discrete fracture network model with, where the domain size is 1 kilometer cube. You can see by different colors shown the fractures that are represented by planar 2-dimensional polygons. Those polygons, they intersect with each other, forming the network. All were isolated, were generated, they were removed because they not participate in the main flow. And each polygon is assigned with its own shape, size, location, aperture, and orientation. So the size follows power law or log normal distribution. Fractures orientation follow a Fisher distribution. The aperture which is assigned to each fracture is a function of fracture size. Like bigger fracture gets in a higher aperture, and as a result, higher transmissivity. So this one is an example of reproducing fracture network of a Forsmark nuclear repository site, that was the data was provided by SKB. So here is a zoom in. Once the fracture network is generated, we focus on producing high quality computational mesh. And here is a zoom in frame of one of the parts of fracture network, and you can see that our mesh coincides along the intersections of fractures, and the mesh is finer near intersections and a little bit coarser as you go far from intersections. The Delaunay triangulations is a base for forming control volumes, which are Voronoi polygons. So Delaunay triangulation here is represented by black lines and then colored lines showing Voronoi polygons. And this is a control volumes. This is a unit for flow solution. Here is an example of our flow solution where the boundary conditions, pressure boundary conditions, are applied to the bottom and the top side as well. They can be applied to any domain side, any side of a domain. The high pressure is applied to the bottom, assuming that flow will be going from bottom to top. And here is how transmissivity is set up. So this is just an example where the transmissivity is given as a constant value per each fracture in the function of fracture size. So you can see here a few really big fractures with high transmissivity comparatively to the small fractures around that have much less transmissive. So in order to calculate the steady state flow solution, we use software called pFlowtran. This is highly parallel and open source code. The next part will be to make a transport. So the flow solution doesn't provide us Darcy velocities in every computational cell. Instead, it provides the mass flux as scalar values for every edge of control volumes. So we use a reconstruction of Darcy velocities in order to get a Darcy velocity in each cell center of our computational mesh. And then we use predictor-corrector method to get a transport. So in this example, you can see 1,000 trajectories of particles that all particles started from the same region on the bottom, and then they diverge pretty fast and they follow to the bottom, to the top of outflow boundary domain. The travel time is measured on a boundary domain, and then here you see the CDF distribution of travel time, and we can analyze actually the real transport of it. So let me go back to our reservoir modeling, where the particles and transport represent some amount of methane gas. So here is a cross-section of our DFN. There we have horizontal well and hydraulic fractures. This is red lines that are placed in 30 meters in between each other. The domain size is 200 by 200 by 200 meters. And two sets of natural fractures, one of them oriented more or less parallel to the well and other perpendicular. So the next movie would tell you better about our model. So there is a well, there is 6 hydraulic fractures that placed perpendicular to the well. And here is a color shows the pressure solution, pressure gradient to all natural fractures around. And then particles are seated randomly. So here is an advection transport is shown. So particles are sitting randomly on the surface of fractures. And then they just shows their travel time sinking to the well. Since we want to look at the aperture, how aperture affects on a transport, we are considering 3 scenarios. So the first scenario is we assign the constant aperture over the whole DFN. For each fracture, regardless of its size, it has the same aperture and as a result the same transmissivity. The second case, the aperture is constant along fracture, but it is a function of fracture size. So as fracture is bigger, it has higher aperture and higher transmissivity. The third case, we try to vary, to introduce some internal heterogeneity and to vary the aperture along each fracture. So we use a special correlation length to define for each fracture. So here is like just an example of 5 cases when a spatial correlation length is a function of fracture radius. So here is like 10% of fracture radius, 30, 50, 70, and 90. So if you look at the 10% of correlation length, it's pretty noisy, so it's a big mixture of high aperture and low aperture zones. As you go to higher, to longer spatial correlation length, you can clearly see some zones of higher aperture and higher transmissive zones to a small one. So this is like a third case of it. And once the aperture and transmissivity defined in our model, we apply boundary conditions like high pressure along the well, and the well has a lowest pressures, and particles, as it's shown here, can sink into well. They travel from any parts of the fractures in entire domain when travel to the well. As we started analyzing the travel time of particles, we just saw that varying the spatial correlation length for aperture is not really enough. What is also important is variability. As we increase variability to 4 orders of magnitude, we actually saw that, so here is shown a single fracture problem, we saw the clustering. So for example, in this problem, there on inflow boundary, particles was seeded, they kind of forced to go through the low permeable zone, but then they decide to clustered and go to the higher aperture zones. So this is not enough even to look at higher variability, because it's also important how the pressure gradients fluid pressure gradients is distributed along the fracture. So if just having the same pattern of aperture and applying pressure gradient from bottom to top and seeding particles equally of, for example, on this side, we will have a bunch of particles that will be going only through the hypermeable zones, and they will show much less travel times than those that will be forced going through the low permeable zone. So here is our production curves that we got from our advective transport, and let me start concluding here. So in the first case, when aperture is constant over the whole DFN, it's very different from all other cases, and we don't really see a huge decline and a big tail. But we have to know that this case is kind of unrealistic, because in nature we cannot really see for like equal aperture and equal transmissivity over whole fractures. So for the second case, when the aperture is constant along fracture, but it varies from fracture to fracture and being function of fracture size, we see the decline. And this case is pretty similar to those when aperture varies inside the fracture, but with very low variability. So there is almost no difference. Our conclusion is here that for single fracture problem, it might be important, but in the whole DFN, there is spots where particles and transport goes slowly and then goes faster, but it actually compensates each other if you consider the whole DFN. As soon as we increase variability, this is this line, we see even higher decline, and this is a different from with low variability case, but we should be really careful here in order to not go beyond the realistic variations, because 4 order of magnitude might sound non-realistic for hydraulic fracturing. So people could do experiments, they know better here. So, and of course, we cannot really make a conclusion of natural gas production without looking at rock matrix, because here what you see is the results only for advective transport. So the next thing that we did, we seed particles over the whole domain, not only on fracture surfaces. And we calculate it's from particles the closest distance to closest fracture, the distance to closest fracture, and we use this equation in order to estimate the travel time that needed for gas to go from porous media to fractures. This equation is a function of diffusion coefficient of a porosity of a medium. So I would like to draw your attention that those production curves for different diffusion coefficients actually goes till 100 years. So our next conclusion is that we have 60% of productions in the first year because this is a gas that comes from fractures, with a purely advective transport. The gas that comes from rock matrix, from porous media, goes pretty slow, and it shows up only after first 5 years. And of course, it depends on the diffusion of a shale that you're considering. So my last slide is on references on our software. Thank you for your attention and questions.
Do we have time for questions?
Do we?
Yes.
In the case where you had internal aperture variability, did you have the same mean aperture?
Yes, absolutely. We tried to keep the same mean value in order to compare cases then. Yeah.
Any other questions? The production decline that you see is a lot less than what's seen in other places. I mean, what other physics needs to be put into these in order to mimic those production declines, do you think? Or?
Well, we still have to normalize the mass values, like what kind of mass of gas is represented by our particles and what was absorbed in the field and how people... So
does the physics encapsulated in your simulations cover what's needed to order to predict the decline, or is there more?
We believe so.